Hello everyone, we are Group 7 and our project is about the design of a methanol production system. Methanol is a simple yet very important chemical used in the industry. In this project, we focused on how chemical engineering principles are applied to produce methanol efficiently and safely.
Now for the process flow diagram and its unit functions. So our process flow diagram includes 11 main unit operations. The key components are the reactor, where synthesis gas is converted into methanol, and the distillation column, which purifies our final product. Other units such as heat exchangers, compressors, pumps, and the valves help maintain steady operation. And each of these units work together to make sure the overall process is efficient and safe. Other components to take note of is the flash separator, knockout drum, and the pump. The flash separators separate a liquid vapor mixture by partially vaporizing or condensing the feed using a single pressure reduction step, while the knockout drum removes liquid droplets or mist from a gas stream before it moves to the next stage of the process.
In the mass balance part, we made a few assumptions, including steady state operation with no heat or mass loss to the surroundings. Then, we calculated the non-reactive system to check consistency of the flow rates, and then continued to reactive system where the methanol is formed from CO2 and hydrogen. The mass balance helped us verify that all input and output streams match properly. Let's dive deeper into the mass balance of non-reactive system. The unit operation that we chose is the distillation column. In this part, we calculated the molar flow rates, mass flow rates, mole fractions, and mass fractions of both inlet and outlet using these formulas. Then, these two tables are the result of our calculations. Next is the mass balance of reactive system. For this part, we chose the reactor. We used these formulas to calculate the mass balance, just like non-reactive part, but there's just some addition on this part. As you can see, after calculating, we obtain these tables. So, for both parts in mass balance, we can conclude that all mass in is equal to all mass out.
The law of conservation of energy states that energy cannot be created or destroyed. It can only be transformed from one form to another. In any physical or chemical process, the total energy of an isolated system remains constant. This principle forms the foundation of energy balance calculations in engineering. By applying energy conservation, we ensure that the total energy entering a system equals the total energy leaving the system, accounting for any accumulation or losses. This allows engineers to analyze, design, and optimize various unit operations with accuracy and consistency.
Moving on the fluid mechanics section. This part focuses on how fluid moves throughout the methanol plant. Understanding fluid behavior is very important for designing pipeline, pump, and the storage system. It ensures that the process runs smoothly without pressure losses and safety issues. For the methanol transport within our plant, the design of the piping system was critical for efficiency and safety. So here is our piping layout. we selected the stainless steel 316 pipeline for its excellent corrosion resistance and ability to withstand the process pressure and temperature. A universal pipe diameter of 0.036 meter was chosen as it optimal, helping to maintain a suitable velocity and minimize the pressure drop. Finally, we used the 20 meter pipeline because it is practical distance for our plant layout and long enough to connect the major component. And also, we use 100 meter pipeline to connect to storage tank. So we use this 20 meter and 100 meter pipe because it's enough to keep the pressure drop and cost manageable. This careful selected layout ensures a safe, efficient and cost-effective transfer for our methanol.
In this section, we calculated the pressure losses for 5 different pipelines using the Darcy-Weisbach equation. We applied consistent assumptions such as steady-state flow and used the provided densities, velocities, and pipe dimensions for each case. This let us quantify how much pressure is lost due to friction in each line and compare performance across the system. Overall, the calculations give a clear picture of how the fluid behaves with the network and confirms that our approach is suitable for evaluating pressure requirements in the piping layout.
So for the product delivery strategy, methanol is cooled to a liquid for safe, stable transport, and the second one is short piping run is applied to minimize the friction losses and maintenance, and the third one is a centrifugal pump is selected for continuous flow and efficiency, and the last but not least is low cost, simple and reliable, and ideal for high capacity methanol transfer. So the left side is our key parameters and the right side is the quantity that we have calculated. So next is the pump power dimension and capacity. So the first one will go for the storage autonomy and tank sizing. And if we assume that storage autonomy is 24 hours and the required volume will be the formula V equals to Q times T, and 3.0357, which is the Q, will times with 24 hours, and then will give us the value for the required volume, which is 72.86 meter cube. And then the last one is the design margin. If we assume that it's 50% reserve, then we will be needed 72.86 times 1.105, an approximate of 85 meter cube. And the second one is for the tank dimensions. The volume formula for tank dimension will be V equals to pi d square over 4 times H. So the selected dimension will be diameter 5 meter and height 4.5 meter. So the gross volume will be 88.36 meter cube. And the working capacity will be approximate 84 meter cube with 5% utilization.
To conclude, this project helped us apply what we've learned in both PCE and CEFM into a complete design study. We now understand how different units and calculations come together to create a working methanol production system. Most importantly, it improved our teamwork, problem solving, and our ability to connect theory with real-life engineering design.